And welcome to our next lesson on acids and bases. In today's lesson, we're going to learn about the second main model of acids and bases called the Bronsted-Lowry acid and base model, or sometimes just the Bronsted model for short. I keep saying, if you make a scientific discovery, don't be the second person on the name because that often gets left off when people shorten it. So the Bronsted model is a little bit more generic than the Arrhenius model. Yesterday we saw the Arrhenius model of acids and bases, in which we had water was an important component, and acids released H plus in water, which made H3O plus, and bases released OH minus in water. Now we might see that as well, but it's not a necessary condition. And we will start off looking at water as one of our components of the reaction. So in the Bronsted-Lowry model, instead of worrying about forming H+, we're going to say that acids donate or give or lose H+. And we're going to talk about H+ now as being a proton. Scientists do call this a proton, and in fact, if you remember, hydrogen is a proton and an electron, and so when it loses its electron, all that's left over is the proton, and so we do call this a proton. Bases are the opposite, so this is a give and take now. This is going to be how we define these acids and bases, by one thing giving up and the other thing getting. And so we say that bases accept or gain a proton. And that's how we're going to define these. And in every reaction now in the Bronsted-Lowry model, we're going to have both an acid and a base. So we're going to need an acid and a base. And I'm going to use the colors to indicate acids and bases. And what's going to happen is that the acid has an H in it. So the acid, HCl, hydrochloric acid, has that H in it. That H, and let's label this as our acid, that H is going to be donated, and it's going to be donated to the other thing in the reaction. And now water is important in this reaction, because if the HCl is the acid, the water is what's accepting the proton from the acid, and so that makes water, where's my purple? I thought I made purple. Ask for purple here. Is going to be the base. And what's going to be left over is the Cl is going to be by itself. We've lost an H and we've lost a plus. And so make sure you keep your charges clear. So we're left with a chloride, Cl minus by itself. And we saw this yesterday as well. And that's aqueous. And now we can see that the combination of H plus and H2O makes that hydronium ion as the other product. For bases, we have a similar kind of reaction in which we're going to have water present. And ammonia is a base. And you may have wondered, I think we had ammonia as bases before, why ammonia is a base, since there's no OH in it. And even though there's no H in it, it's no OH in it, it still acts as a base, and it can still create hydroxide in water, and this is how. If it's the base, remember our definition of bases up above is that a base accepts a proton. But now, where is it going to get the proton from? It's going to get the proton from one of the H's in water. And we're going to take that proton and we're going to pull it over to the NH3. And now that makes water acting as an acid down here. We'll talk about the fact that water does two things, two different possible things in a few moments. What's going to be left over when we do this reaction? The NH3 is going to gain an additional H. So we're going to have NH4 plus. That's the ammonium ion. And we'll talk about the relationship between ammonium and ammonia in a few minutes. And what's left over when the water splits apart is hydroxide. And there's where the hydroxide comes from in ammonia. Now, how does this work? The way this works is ammonia, we're going to look at the Lewis structures here. Ammonia has this lone pair of electrons right here. Lone pair of electrons can be very attractive to something that doesn't have any electrons, such as an H+. And there's going to be this tug of war. And this is what's going on with the acids now. Acids and bases are getting into this tug of war with water for one of water's H+. And so what's going to happen is this bond, the OH bond between the H and the O in the water, is going to break apart. And what's going to happen is that positive H+ is going to get pulled over, going to get attracted to that lone pair of electrons on the ammonia. Meanwhile, what's going to be left over is going to be this guy. And that guy is going to form hydroxide. And so the reaction is going to end up creating ammonium, the NH4 ion, which is a tetrahedral polyatomic ion. If you remember back in our days of looking at Vesper, the ammonia was trigonal pyramid, and now the ammonium is tetrahedral. Because it was an ion, we've got to put our brackets around it. So there's our ammonium ion. And the hydroxide ion, the O and the H, the oxygen now has 3 lone pairs on it. And if you count up all your electrons and your charges, you'll find that gives you a negative charge. And so that's what's going on whenever we have ammonia. In fact, any molecule that has nitrogen with 3 bonds and 1 lone pair of electrons will be a base. And there's going to be a homework question, which is going to have you investigate that with another compound related to ammonia. Now, water. We saw water acting as an acid. In the second reaction, we saw it acting as a base in the first reaction, and it depends on the chemical it's with. If it's with an acid, it's going to act like a base. If it's with a base, it's going to act like an acid. And that has a very special name in chemistry. We call that amphoteric. Amphoteric. And amphoteric is just any compound that can act as either an acid or a base. And we'll see more of these later on as well. So going through this reaction, these reactions have products which are also important to us. Products, things on the opposite side of the reaction. These are called conjugates. And the conjugates form conjugate acid-base pairs. And with acids and bases, they always come in these pairs. And the way we recognize the conjugates, and you're going to have to do some of this on the homework, is that the conjugate base is what is left. So the conjugate base, remember again, these are products. So you start off with the reactants of the acid, and the conjugate base is what is left after the acid loses an H+. And likewise, the conjugate acid, you start off with the base and what is formed when the base gains H+. So they always come from, they come from the opposite. An acid forms the conjugate base, a base forms the conjugate acid. And we'll do a little bit more work with that in a few moments. But let's go back up to our first reaction and see if we can identify the conjugate acid and the conjugate base, because there's going to be one on each side. So let's modify this. We need an acid and a base on both sides of the reaction. And just the fact that it's on the product side makes it a conjugate. So if we start off with HCl, let me change colors so that I can color code these. If we start off with HCl, what is left over after we lose the proton is the Cl minus. And so that makes the chloride our conjugate base. I'm going to abbreviate because conjugate is a long word to spell out. All right, so we have that conjugate base there, which means that the hydronium must be the conjugate acid. But let's just investigate that to make sure we understand why that is. So when we have water, we have 2 protons, 2 H's on it. When we have the H3O plus, we now have 3 protons. We've gained a proton, we've gained an H, and we've gained a plus. And so that means that this is the conjugate acid. Pause for a moment and see if you can figure out in the ammonia reacting with water, which one is the conjugate acid and which one is the conjugate base. So pause for a moment, see if you can figure it out, and then come back. Okay, so hopefully you've come back now and you've correctly identified. Notice that the ammonia starts off with 3 H's on it and it ends up with 4 H's. So it's gained a proton, and that's what we saw in the reaction, gaining a proton. So since our definition is that the conjugate acid is what's formed after the base gains a proton, the ammonium must be the conjugate acid. And so it turns out that there is this relationship between ammonia and ammonium, that they are conjugate acid-base pairs, and ammonium is the conjugate acid of ammonia. You can also say that ammonia is the conjugate base of ammonium. Meanwhile, the water started off with the OH had a proton on it. Now the OH doesn't have a proton. It's lost a proton. And so the conjugate base, I should be using the same color that I used up above. Let me try erasing that without. Okay. So we have the OH here, we have the OH here, and so that makes the hydroxide conjugate base. Now, a couple of important points to make. Number one, whenever you have, now you're not always going to have H3O plus in your reaction, but if you have H3O plus, it's always going to be either the acid, you can have it in the reactants, or the conjugate acid, because it can only lose an H plus. Even though there's room for another H on H3O plus, what turns out is that the charge is too high. So it has a positive charge. You're not going to be able to attract another H plus to the H3O plus. Hydroxide is always going to be either the base or the conjugate base. Again, you can have it as in the reactant side as well. And that's because it can only gain a proton. And so the definition of conjugate acid-base pairs should show you that the conjugate acid-base pairs are always going to differ by exactly 1 H plus. The base has an extra H plus. So up above we saw HCl was the acid. We remove that H plus and we make Cl minus as its conjugate base. If we tag water as a base, water as a base is going to accept a proton. We're going to add an H2 there, and we're going to make that H3O and plus. Please don't forget these signs. Remember, it's an H plus, this H plus that differs between the two of them. So we're either going to have an extra plus charge in the conjugate acid, or missing a positive charge in the conjugate base. If we tag ammonia as a base, its conjugate acid, we're going to add 1 H, and we're going to make NH4 plus. And water, if we tag that as the acid, we're going to lose 1 H, only lose 1 H, and make OH minus. Just a little note here. H3O plus and OH minus are not conjugates. They're not conjugates because they differ by more than one H plus. And in fact, you have to have water in between the two of them to get from one to the other. Okay, before we do any more work, let's see if you can figure out, based on the definitions, what the conjugate base of acetic acid, so this is an acid, what's the conjugate base of acetic acid? In other words, what's left over when you lose the H plus? So pause the video now, see if you can figure out the answer to that. And I've given you acetic acid in two forms here. We're gonna answer both forms here. All right, did you figure it out? So we pull that H plus off. What's left over after the acid loses its H plus is going to be C2H3O2. Don't forget your minus sign. That's the acetate ion. Or we can write it as CH3COO with a negative sign there. And either one of these is acceptable as a form of writing the acetate ion, that conjugate base of acetic acid. Here we have hydrogen carbonate. Hydrogen carbonate, now we'll talk more about this in a future lesson, but hydrogen carbonate is actually amphoteric because it can lose a proton that it has here, but I'm telling you that this is acting as a base. So now we're acting as a base. So I want to know what's the conjugate acid. In other words, when we can add a proton to that, and you can recognize you can add a proton, one of the ways you recognize it is a negative charge. If you've got a negative charge on one of these guys, generally it can act as a base. It doesn't have to act as the base. In this case, it can act as the base. So pause the video and see if you can figure out what the conjugate acid is. So hopefully you realize that we're gaining a proton. So we're going to add a proton here. We have a single proton here. So all we're going to do is write that we've got two protons, H2CO3, and the negative charge is going to go away, and we're going to get an overall neutral charge because the negative of the hydrogen carbonate and the positive of the hydrogen ion have canceled each other out. Here's a practice problem. It has some similar things in it. Notice there's no water present. And so we're going to do this reaction without having to worry about whether water is present or not. Now, you may say, how do you know which one is the acid, which one is the base? In this case, it's pretty straightforward. Only one of these guys has an H plus that can be lost. And that would be this guy. This is called propanoic acid, which you don't need to know. Now notice it's the H in front that's being lost. Those 5 H's are attached to carbons. So like we saw yesterday with acetic acid, those carbons, the carbon-hydrogen bonds, first of all, there's no acid-base properties with carbon-hydrogen bonds. And second of all, there's no room on the 3 carbons for additional hydrogens to go. So there's no room for a hydrogen to go on there, and you're not going to take those off. Meanwhile, SO3 2- has no protons that can be lost. So SO3 2- has to be the base. So let's label that as the base, and let's label propanoic acid. Oh, there's a giveaway, right? Propanoic acid as the acid. Let's take that proton and donate it over to the base. This donation always stays on the left side of the arrow. It's always showing where that proton is going, not where it has ended up, but in the products, but where it's going in the reactants. All right, so on the right side, the propanoate, that's a mouthful, C3H5O2 is left over. We've lost a proton, so it's a negative charge, and that's aqueous. And the sulfite has gained a proton and made HSO3 minus, gained a positive charge, and that's also aqueous. And if we look, I'm going to label these with blue, with red and purple again. So the base becomes the conjugate acid. So label this as the conjugate acid. And the acid becomes the conjugate base. So we'll label this propanoate anion as our conjugate base. And then when we identify the acid-base pairs, we have the sulfite, since I've got purple right now, is going to be our base. Oh, you know what? That was a typo. That should have been a 3 and a 5. Oh, sorry about that. It should have been a 3 there. The propanoic acid was our acid. And you notice I'm now abbreviating acid base, conjugate acid, conjugate base. The products, actually, let's keep it red. HSO3 minus is the conjugate acid of the sulfite ion, and C3H5O2 minus is the conjugate base of propanoic acid. In the homework, I will either give you the product to help you figure out what the acid and base are, and that'll be one set of the problems, or I will label the acid and the base so you know which one is gaining and which one is losing, and I'll have you determine what the products are of that reaction. And there'll be some other problems identifying conjugate acids, conjugate bases, and things like that. So do well with the homework, and we'll see you next time in class.